Hello and welcome to Linear Algebra for Economists. In this presentation series, we will be exploring how linear algebra might be a useful tool under your belt as an economist. Whether you're a student of economics or someone just curious about how mathematics applies to real-world scenarios, I hope you will be finding this video series useful. Short disclaimer before we begin, I myself am an applied mathematician and mathematics teacher, and I'm not an economist. So if you're an economist and at any point in the series you have different examples or anything to add at all, feel free to let me know down in the comments. Also, if you have any questions, particularly if you're a student of mine, feel free to ask any questions in the comments below and I will be doing my best to respond. Now, without further ado, let's begin with why I believe you might want to learn linear algebra as an economist. Linear algebra deals with mathematical tools and concepts that are foundational for solving a variety of mathematics problems that can relate to economics. Its concepts are found all over in higher mathematics. Just as basic algebra forms the basis of high school mathematics, linear algebra is at the roots of many of the topics that you will be finding in higher mathematics courses. Whenever we have to deal with multiple variables at the same time, such as modeling phenomena, analyzing economic systems, and so on. It also forms the basis of linear and convex optimization, where we seek to maximize or minimize an objective function such as profit, utility, or costs. Further examples involve the study of dynamical systems, which, for instance, the economy is a pretty big example of, and game theory, which deals with strategies of interactions between rational agents. Let's dive into the concept of vectors, which is the most basic concept in linear algebra. Imagine you're comparing the costs of renting office spaces. Renting a 160 square meter office with 2 conference rooms in one building costs €2,000, while 180 square meter office with 3 conference rooms in another building costs €2,340. How can we handle such data? Well, first we need to decide which data we care about. Does the number of conference rooms matter at all for us? Does the area matter, or are we just looking for conference rooms? Or does the price matter at all, or do we have infinite resources in that regard? Also, if we choose to represent €2,000 for a 160 square meter office, we have to stick with that convention. It's because that's a distinctly different scenario from €160 for 2,000 square meter office, obviously. So for the purposes of economics, vectors are ordered lists of quantities where the order of elements does matter, like we said before. Now, for physicists and engineers, vectors also have some real-world objective meaning, such as the velocity of a particle, which is some quantity irrespective of the numbers we choose to associate with them, but we don't worry about that in economics usually. Now suppose that you have €10,000 in a month to rent out offices in office buildings, and we currently have 200 square meters of office space and 4 conference rooms at our disposal. How would these numbers change if we rented space in one or both of these office buildings? One can easily and efficiently track these changes using vector operations. Here's how it works. If you rent one more unit in building A, your available space and conference rooms increase while your budget decreases. Similar calculations can be done for building B. And in general, let's take a look at vector operations for a second. So let's suppose that we have a vector v, which is represented by this list of numbers, which is a vector, and then alpha, which is some number or scalar. Then we can multiply these two quantities together, and the way we do that is element-wise, we multiply alpha into all of the elements in v. This is usually represented by alpha times v, or sometimes even v times alpha. And this is, of course, a new vector. We can also add vectors together. So if we have, let's say, u and v, which are 2 vectors of the same length, like remember they both have d components, then we can add them together. And what we do is we add them coordinate-wise. So the sum of u plus v, or v plus u, doesn't matter, would be u1 plus v1, u2 plus v2, and so on and so forth. And like I said, you cannot add vectors of different shapes together. We can keep repeating such operations one after the other, and that will give us the concepts of linear combinations. So if we have a bunch of vectors and then the same number of scalars, so we can multiply the first vector with the first scalar, second vector with the second scalar, and so on and so forth, and then just add them together, giving us in general a new vector. And from now on we will be writing vectors as columns instead of rows. This will fit more nicely with the idea of matrix multiplication later. So for example, a linear combination, if we have the vector 1, -7 minus 2 times -6, 2 plus 3 times 0, 9, we add and multiply these coordinate-wise, and if we crunch the numbers, we should get another vector, in this case 13, 16. We can also define vectors using index notation, which helps in describing vectors. So for instance, if I say that Vj is equal to j, that means that the first index is 1, the second index is 2, the third index is 3, and so on and so forth. And at this point, I would need to specify how many indices I actually have. So that's why I said that this vector is in R3. So it has 3 components. So this is what it would look like. For a second example, I could also say something more complicated, that let's say Wj is j squared minus 1. So for j equals 1, this would give us 1 squared minus 1, which is 0. And then for j equals 2, this is 2 squared minus 1, and so on and so forth. I specified that this should have 5 coordinates. So altogether we would have 0, 3, 8, 15, and 24, which are just one less than each of these square numbers. Special objects like the Kronecker delta and others are sometimes also used in calculations. So instead of saying that this number is 1 if and only if both of these indices are equal to each other, otherwise they are 0, we can just say that it's the Kronecker delta of these two indices. So the Kronecker delta is going to do exactly what I just described. So it's either 1 or 0, depending on whether or not these two indices are equal to each other or not. So this is not a vector, but this has 2 indices. So this is going to be more like a matrix or a tensor. So examples include delta 1, 1 equals delta 5, 5 equals delta 9, 9. So in the case where these are equal to each other, then this will return 1, and in any other case, this will return 0. Canonical basis vectors are also objects that will appear often. So this is E1, E2, all the way up to ED. These are going to be unit vectors where AJ is all zeros everywhere except at the jth position. So examples include E1, E2, E3 in 3 dimensions, as seen in the screen. Our last example of a special vector is the full ones vector, often denoted by a bold 1. And unless this is obvious, we would need to specify how many coordinates this vector has. Examples include these lovely objects. Finally, let's discuss the dot product of vectors. I claim that every one of you has faced a dot product before the last time you went to the grocery store, so you might have seen something like this. So the dot product of two vectors gives us a scalar value, which can be interpreted as the weight sum of the components. So for example, if Alice goes shopping, the total cost can be calculated as the dot product of the quantity and price vectors. This operation has numerous applications in economics, particularly calculating costs and revenues. So here we'll take the number of loaves of bread, multiply by the cost, and then add the number of boxes of milk that she bought with the cost, and so on and so forth. So this is what the clerk would calculate. So the dot product of two vectors, let's say that we have two vectors of the same length, and then the dot product is going to return us a number, which is as we've seen before, the sum of the product of the respective coordinates. And to make this more compatible with matrix product, which is coming soon, we will be writing this first vector of the dot product as a row vector and omit the multiplication sign. Okay, so examples. The vector 1, -7, dotted with -6, 2 is going to return us -20. If we dot 2, 0, -5 with -1, 9, -2, we would get the number 8. And then we can ask what happens if Alice has several shopping lists and perhaps different supermarket options. Then that's going to leave us with matrices, and that will lead to matrix multiplication, which we will learn about soon in the next video. See you then.